Hi. The second MSI elements that we're going to examine in this video is multiplexer. This is another common MSI element that we use. Let's start from the smallest size multiplexer, which is 2 times 1 multiplexer. That's that one. And then we are going to see 4 times 1 multiplexer. And 4 times 1, and this is 8 times 1 multiplexers. So the size is increasing, so we will be examining all of these. And then we are going to use these muxes for the design of Boolean functions. So let's see it starting from the simplest one. 2 times 1 multiplexer has got 2 inputs and 1 output. In addition to those information inputs, there is a control input which is called select control input. We already said that for MSI elements, since there are many number of gates in it, in an integrated circuit, we've got additional inputs to the information inputs. These are, I call those inputs information inputs. This is just for the control the inputs and plus changes the function of the MSI element. That's why we call it control input. If we were draw a truth table for this logic circuit, it was going to have the total number of inputs is 3, so S, I0, I1, and the output is just 1Z. So a truth table is going to have 8 lines here. So instead of writing a truth table like that, we are using this function table. That's the function table. So when you look at the function table, we can say that when the select input is 0, select is 0. So that I0 input is going to be seen at the output. You see here, Z is equal to output I0. So whatever information you have in that I0 input is going to be transferred to the output if the select input value is 0. If the select input value is 1, then I1 input is going to be transferred to the output. So from this function table, I can say what this element does. If you look at the truth table, it's not easy to say that. That's why we are preferring the function table rather than truth table. Function table tells me what the circuit does. So how does it do that function? So you could see it here. When you select is 0, that was black one, select is 0. Then this input is 0. Whatever the other input is, this AND gate is going to give a 0 at the output. So when the select is 0 here, the NOT gate is going to transfer that 0 to 1. So the input of this AND gate is going to be 1. The output of this AND gate is 1 times I0 gives you I0. I0 plus 0 gives you I0. So when the select is 0, then you transfer this input to the output, as it is said here. It says here. If you choose the select input as 1, select is 1, then this is going to be 1, the other one is going to be 0, isn't it? The output of this NOT gate, when the input is 1, when the input is 1, so that's going to be 0 output. When the input is 1, this is going to be 1. So if this is 1, 1 times I2 gives you I1, sorry, not I2, that's I1. So this input is 0, multiplied with I0 gives you 0. Addition of those two, this is OR gate. At the output, I'm going to have I1. So when you select S as equal to 1, then I1 input is transferred to the output. This is what it says here in the function table. So if you consider this element altogether now, it becomes, this is a 2 input, 1 control input, and the output. So we show this mux element in that form. Okay, so let's come to the higher size muxes. So this is 4 times 1 mux. 4 times 1 mux has got 4 inputs. Let me draw it in a better way. 4 inputs. Let me clear this. And this 1, 2, 3, 4, I0, I1, I2, I3 inputs. These are the information inputs. And there are 2 select inputs. So this is S1 and S0. And 1 output. So this is 4 times 1 mux, or 2 to the power 2 times 1 mux. That 2 tells me the number of select inputs. That 4 tells me these inputs, 4 of them. This one here shows me the 1 output. So the function table is given here. The circuit inside of this 4 times 1 mux is this. So we can follow it now. So you can follow it when both of them 0. That's going to be the prime of the complement of those zeros is going to be 1, 1. 1, 1 comes here, multiplied I0 gives you I0. When S1 and S0 is equal to 0, then this line information is transferred to the output. So it goes like that. So when both of them 1, 1, I3 information is transferred to here. So you can show it with different colors. So that's okay. So when it is 0, 1, when this is 0, 1, this I1 is going to transfer to the output. When this is this one, 1, 0, when you apply 1, 0 here, so this line information is going to transfer to the output. When it is 1, 1, select input 1, 1, so I3 information is going to be transferred to output, I3. So this is a 4 times 1 multiplexer. So it is in an integrated circuit, it's going to be like that. So where we could use these muxes. So what is the application of these elements? Let's come to that point and then I'll show you how you're going to use these elements in order to design a function. So look at, there is a 3 variable function here. These are the variables and this is the function value. That's the truth table, isn't it? So now we are saying if you got 3 independent variables, 2 to the power 3 times 1 mux is enough to design this function. Why is that? If I write the order here is the binary order, start from 0 up to 7, I0 up to 7. So for these inputs, my output is listed here. So I'm going to transfer this output directly to the input of my mux. Now I am saying the output of this mux is f function. Could I say that or not? The answer is yes. How I can say that? When this all I have chosen these independent variables as S2, S1, S0 select inputs. So this is X1, X2, X3. When all of them 0, that means that line, the first line information is going to be transferred to the output as F. So you could see it. I transferred that 0 to here. So when you come to the, let's change the color. If it is 0, 0, 1, so that means that line here. The second line function value is transferred to here already. So if you apply this select input this, if you choose the select input values like that, so the second line information is going to transfer to the output as my function output. So if you continue like that, you're going to see that this truth table here, that part only, has been transferred to the output as the function. So that is the realization of your function. So this is the function table of a 8 times 1 mux. Select input 0, I0 input transferred to the output. Select input 1, 0, 1, that is I5 input is going to be transferred, I4, I5. This is transferred to that. That is the function table for a 8 times 1 mux. Yes. Now we can make a conclusion out of this, saying that any n variable function can be designed by using only 1 to the power n times 1 mux. So that was 3 variable here. We use 2 to the power 3 times 1 mux. So when it is n variable, 2 to the power n multiplied to 1 mux is enough to do the design. Now at that point, let's compare the design that we use in SSI elements and the design we use with the decoders. In the SSI elements, we have found the minimal function and realized the minimal function, saying that the cost made minimal. In here, we don't have any problem like that, because when we buy this mux, is available in the market. So you're going to buy this mux. When you buy this mux, you don't have to find the minimal function. So you can directly transfer this truth table last column to the input of the mux, then you realize your function. You don't have to find the minimal function. So it is much faster to do the design by using this mux. Then you might ask why we learn the SSI design techniques, which is Kuimak-Klasky method and the Carnot map method, to find the minimal function and realize the minimal function instead of the original function. The reason is that if you're going to produce 1 million of a function, if you're going to do a production of this, you need 1 million of those. Then you've got to use the SSI design, because in the SSI design, the number of gates that you're going to use is going to be minimal. So the cost is going to be minimal. So in this case, it is not these components, SSI components are available. So by using the SSI components, you're going to make an integrated circuit. This is called ASIC technology, application specific integrated circuit design. So when you find the minimal function for this 1 million function to be produced, find the minimal function of it. Let's say one gate you saved. So that means totally 1 million gate you have saved. So cost is less. So if you send your minimal function realization to these firms which use this technology in order to produce an ASIC application specific integrated circuit, then they make an integrated circuit based on your minimal function. So the cost of these um, integrated circuit is going to be less than this MSI circuit realization. Okay, therefore we are giving you two of them. So you might ask then why we are using muxes. So assume that you need a function to design for your prototype production. Prototype production means in the research you need a circuit. So for this specific research, you're not going to produce many of them. So in this case, you don't have to spend time to find the minimal function. You can get this MSI element from the market and do this connection and realize this function. So it is much faster to do the realization. But in this case, this is not a max usage realization is not realistic. That's why we are teaching both of them. Let's come a bit further. Next question is this. So still we've got 3 variable function, but assume that we don't have 8 times 1 mux. This is not available in stock, not available. That means not in stock. So assume that you've got 4 times 1 mux available in your stock. So you've got this mux. So this is the function table of this mux. What it says, when these variables are select inputs as far as to 0, 0, so that information transferred is like that. So that's the definition of it. That's definition. You might also call it definition or the function table. Function table. So it is possible to answer to that question. So you can design the 3 variable function by using a smaller size mux. How we are going to use it? So we are going to choose, these are the independent variables, the first 2 variables as S1 and S2, S1 and S0. So that's 1 and that's 0, isn't it? So if you choose that, this is the truth table of your function to be designed. So you are dividing your truth table in 4 groups for the select inputs. This is one group, that's the other group, that's the third group, that's the fourth group. So when you choose these independent variables as the select inputs in your mux, so you're going to determine the input values for your mux. When this S1 and S0, in other words, X1 and X2 variables 0, 0, that means you are in this area. 0, 0. So if you compare the non-use independent variable with your function, in this subgroup, the function value is the same as x3 independent variable value. So that means function is equal to x3. I know that on the other hand, this mux, if the select inputs are 0, 0, then I0 input information is going to be transferred to the output, so x3 is going to be transferred to the output. That means f equals to x3. That's what this one is. If you choose your select input, let me change the color, 0, 1. So that means you are in this subgroup. For this subgroup, if you compare the x3 variable with your function, so it is the opposite of the x3 value, isn't it? Function. So that means function for this group is equal to x3 prime. So on the other hand, in the mux, if you choose this select input 0, 1, this x3 line this second line information is going to be transferred to the output. So if you choose this x3 as the second line information, so you're going to observe at the output x equals to x3 prime, which is this group, isn't it? So this second one, or let's come to green one, okay? So if you choose the select input 1, 0, select input 1, 0, so that information is going to be transferred to the output. So what happens in the graph here, the function value is 0, whatever the exterior value is. So that means it is independent from the x3 input variable, that function value equals to 0. So if I write the third line information as 0, so for this select group, my output is 0. That's my function. So the last one, make it a different color, make it yellow one. For this group, if you choose the select inputs 1, 1, so function value is independent from x3, but that value is equal 1. So if I put that 1 to the input of my last line of mux, so this one is going to be transferred to f if the select inputs are 1, 1. So that means what you observe at the output of these 4 times 1 mux is the same as my function. So we realized a 3 variable function by using a lower size mux. Conclusion is this. So in here we can say that any 3 variable function, can be designed by using a 4 times 1 or 2 to the power 2 times 1 mux and 1 NOT gate. Why I said so? In here, when I choose these select inputs as my independent variables, 2 of them, there is 1 left. So I am comparing my function value and the x3 independent variable value. So my inputs has got x3s or x3 primes. For x3 prime, this is the independent, for x3 itself, since it is independent variable, you can connect this input directly to that I0 line. But in here, in some cases, you might apply x3 prime. To get that x3 prime, you need a NOT gate. So for my mux, since I am using for the information inputs independent variable, only one independent variable, which is x3 in this case, I need the x3 prime as well. For any time I need a x3 prime, I need to use a 1 NOT gate. Since the variable is 1, only 1 NOT gate is enough for me to do that design. So that is a conclusion. So if you compare this one with the previous one, so this one here, use only 1 mux here, but in this one, I use the mux plus 1 NOT gate. So the cost a bit improved in this case, but the cost of this 4 times 1 mux is less than the cost of 8 times 1 mux. So you can compare those two. So let's go on to the last one here. This is an example, another example, but in this case we've got a 4 variable function here. We have chosen these independent select input as the independent variable. So the select input as 1, let's say x2, no, let's make it S1, S2, S3. So we have chosen the select input as those three independent variables. So what is left is x4 variable and the function. So if you use the three select inputs, so you're going to divide this function truth table to 8. One, this blue one, that's the orange one, green one, blue one, green one, light green one, dark green one, I don't know what the name of violet, and the black one here. These are 8 groups. For each group, I'm going to compare x4 variable value and the function value, write it here. So in here, it is independent from the x4 variable, so f equal to 1, it goes like that. If you transfer all this information to these inputs, as we have done it here, that's 4, that's 5, that's, just a moment, this, then this is that one, this is that one, this is that one, and this is that one. So like the previous one, you can design any 4 variable function by using 8 times 1 max plus an AND gate, isn't it? So the previous rule is true in here as well. So when you compare this function realization by using max and by using the decoder, you can say that in the decoder case, if you're going to design more than one function, in addition a decoder, only one decoder, you're going to use OR gates for each function that you're going to design. In here, by using max, you can design only one function, not more than one function. So for each function, you've got to use a max. So conclusion is this: if you're going to design more than one function, decoder usage is preferable. If you're going to design only one Boolean function, that max is preferable. You might say a conclusion like that. So that's the end of this video then.